how do I read this table? So they call it, like I said, there's kind of two ways you can call it: a contingency table, or they'll call it a two-way frequency table. Basically what it does is it shows at least two different categories. It could be more. So like you could have 3 categories and 2 or something like that. So this one, the first little example I have, just male or female, and then right-handed or left-handed. So it's just 2 categories here, what hand you use, and then gender for this particular table. Now, basically the information, which they don't always give you all of it, they don't always give you the totals, they might just give you kind of what I put a little box around here. So this is the data. So across the top, so you got like 43 guys that are right-handed, 9 guys that are left-handed. That's kind of how you would read it. The total goes across, so I'm adding 43 and 9 to get 52. You can do that down the column as well. So like this is breaking it down. You got 43 guys that are right-handed, 44 girls. The total number of right-handed people is here. Now, whenever you're doing this, the total number of people that are in the data that you have will fall in this bottom corner, and it should match. So whatever you get from the, it's not always 100, it could be a different number, but what I'm saying is the 2 right hand and left hand added together should be 100, and then the male and female added together, they should be the same number if you add them. So how many people are represented in the survey for my little example here? This is 100. Okay, just looking at the table, can you tell me how many people are girls? The total right there, 48. How many guys? 52. How many people total are right-handed? 87. The total in the bottom right there. How many people are left-handed? Okay, not terrible to read. So we're just looking at that to make sure you guys can read it. We're going to actually use it to do some probabilities here in a second. Okay, so see if I can kind of keep that table up on the screen so we can see it. All right, so what is the probability I randomly pick somebody and they are right-handed? Right-handed. Randomly pick somebody out of this table, they're right-handed. 87 out of the total. All right, if you're into a decimal, that is 0.87. What is the probability I randomly pick somebody out of this table and they're a girl? 48 over 100. I know I can reduce that fraction. I'm just going to write the decimal be 0.48. Okay, now, what is the probability, this is a little trickier, that they are male and they are right-handed? Ty, what do you think? Exactly. So like that 43, that's male and right-handed, all in that category right there for you. You're just going to pick it out, 43 out of 100, and 0.43 is the decimal there. What's the probability we would randomly select somebody from here? They'd be female and left-handed. There's only 4, so female and left-handed is right there. 4 out of the total 100. So this would be 0.04 as a decimal. Okay, now this is a little trickier. So what's the probability I pick somebody that's a guy or left-handed? So let me just go through real quick. So are these two, see if you remember from yesterday, are these two things mutually exclusive? So can they not happen at the same time? They can happen at the same time. So these are not mutually exclusive, so there's a little overlap here. So you got to think about this. Okay, probability, I just grabbed a person from this table and it's a guy. You got 52. The probability that I grab somebody from this table and they're left-handed, they are 13. Or there are 13, I can't speak. Okay, what would I do to that to take care of the overlap? Yes, subtract the left-handed guys because I'm counting them twice. So we're just going to subtract 9 from that. And that would be what we have on the top of our fraction. And I'm using a calculator. Don't judge me. Okay. And I didn't do it correctly. So perfect. So this total here, we get 56 out of 100. If you like the decimal better, that's 0.56. All right, so I'm trying to keep the table on the screen here. Can I be a girl and right-handed? So they're not mutually exclusive, so there's going to be an overlap. So if I do probability here, if I just pick a girl, it'd be 48. If I pick somebody that's right-handed, it would be 87. And then we have to subtract off the overlap. So basically I have to subtract off the girls that are right-handed, which would be 44 because I counted them twice. So I'm going to do 48 plus 87 minus the overlap because I counted those people twice. And I'm going to get yeah, 91 out of 100, so 0.91. Okay. So as I'm doing that, what I'm subtracting is the group that I counted twice, which would be overlap. So like here, I'm the overlap female and right-handed. The overlap here, male and left-handed. You're subtracting off that overlap to get your percentage. Okay, now we're going to talk about, this is the last new thing we're going to talk about, which is conditional probability. All right, now probability in event B, this will be the second event, will occur given that another event A has already happened. So given that this has already happened, and it can only exist when two events are dependent. So the outcome of the first event is going to affect, or the probability of the first event affects the probability of the second. Okay, you write conditional probability. This is how you would write it in the notation here. This is like a capital P with parentheses. You see a B, and then there's kind of like a longer bar. It's just like a straight line, and then an A. This is the notation. The way I would read that, it's the probability of B given A is how you would read that. So the probability B happens given that you know A has already happened. Okay, now I'm going to give you the formal, here's how you would find this, and then I'm going to show you kind of how to do it a little quickly with the lovely contingency table. But the technical definition here, this is a fraction. So it's the probability, and they write it like this. It's like an upside down U shape. So this is it's called an intersection. So basically it works for both is what it would be. And then divided by the probability of A. Okay, so I'm going to show you with the formal definition, and then I'll show you how I do it with the contingency table because I think it's way easier. Okay, if I use the same table we had at the top, this says the probability I select somebody that is right-handed given that they were female. Okay, the intersection would be a probability, right? The intersection meaning both are happening at once. So right-handed and female would be this. It would be 44 out of 100. Divided by the probability that I just picked somebody out of the table that's female. There's 48 in the table here. And what I'm going to show you, if I do my keep, change, flip, you're just going to cancel the 100s out. So you'd have 44 out of 48. So I'm taking the intersection, so it's right-handed and female is what I did on the top. That's that top probability. And the probability of that given event. Now here's what I do, especially if you have a table. Okay, here's what I look at. I say, what is the given part? So given that the person was female, so like I don't even look at that part. I just look at the line where I have girls. So given that the person's female, what's the probability that they were right-handed? Then it would be the 44 out of 48. So if you want to do it like that, I think that might be a tiny bit easier than using the formula because you could just pick it out of the table. So like if I was doing this one, probability I pick a girl given that they were right-handed. So I literally just cover up the left-handed. So given that they are right-handed would mean I'm going to put the 87, whatever the given is on the bottom. There's 87 right-handed people. How many of them are female? This would be 44 out of 87. If I do left-handed given that they're male, I would just cover up everything except the line where we're talking about guys. So given that they're male, there's 52 people in that table that are male. And the probability I grab a left-handed person would be 9 out of 52. Okay, and then if I say right-handed is given again, so I'm right-handed, so I'm only got 87 people to pick from. What is the probability I picked a guy? That would be 43 out of the 87. That might be a little bit easier. Just take the given, whatever the given is, that goes on the bottom, and then just cover up the rest of the table. Does anybody have a question? Okay. The other thing I'm going to show you here real quick is how to do a probability tree, which I've got a lovely example here for you on the back, but you can do conditional probabilities in this. If you don't have a table, you can make a little tree. So this is just giving an example of flipping a coin. Okay, so here's the tree diagram. Basically, you start here, we're going to flip a coin. So there's only two outcomes that can happen if I get a coin flipped, and that's heads or tails. And what they do is they write the probability along the line, and then whatever the outcome is at the end of it. Okay, now, if you want to come over here, this one's a little bit more complicated. So this is showing several tosses. So this is like, I flipped heads or tails, and then it's tossing the coin again. So again, heads or tails. So it's showing you two flips of a coin, all the possible outcomes. If you want to calculate the probability, if you go along the branches across here, you multiply them together. So like if I wanted to do probability I flipped heads twice, I would do 1/2 times 1/2 till I got to the end of the branch. Or if I wanted to do, okay, probability I flipped heads then tails, be 1/2 here, 1/2 here, that would be the result. If you add down kind of like the different sets of the branches, you can, maybe don't, let me grab a highlighter here, because I'm going to kind of split this down here. If you go top to bottom, if you add them, that will give you the total in terms of the probability. So you can see it at the end here, multiplied, and you can add down the column. Each branch should add up to 1. So we're going to make one here. I promise I just made that sound really terrible, and it's not. So this says, school system compiled following information from a survey of people who were juniors 10 years earlier. So 85% of the students graduated from high school. Of the students who graduated, 90% are happy with their present job. Of the students who did not graduate, 60% are happy with their present job. Let's draw a diagram for the situation. Okay, so I'm just going to start like, here we go, just kind of like a little dot, and then I'm going to draw a line here, or like a little ray almost, and one here. So first thing it says is 85% of these people graduated. So the result would be I either graduated or not. I didn't graduate. All right, the probability I graduated would be 85%. What would the probability, or what would the percentage be, or the decimal be, for the people that did not graduate? 15. So this would be 0.15. Okay, so it says of the students who graduated, so I'm working on this top branch here. So then we're going to split off. It says they're either happy with their job or they're not happy with their current job. So it tells you 90% are happy, so that would go along that branch. What would you put along the branch for the people that are not happy with their job? If I put 0.9 for they're happy, what would you put for not happy? 0.1. They have to add up to 1. So like 0.85, 0.15, that adds up to 1. 0.9, 0.1, that adds up to 1. So like that little branch has to add up to 1. Okay, then it says of the students who did not graduate from high school, 60% are happy with their present job. So didn't graduate, and then again, the outcome is either they're happy with their job or they're not happy with their job. So it tells me 60% are happy with their job. So then what percent are not happy with their job? 0.4. Okay, now here's all you're going to do. Some of these are conditional, some of them are not. So this just says they graduated and they're happy with their job. So you're just going to follow along the branch and you just multiply them together. So graduated here would be 85% or 0.85, and they're happy with their job. So you would take the 0.85 and just follow along that branch and you multiply as you go across. So I would do 0.85 times 0.9, which is going to give me 0.765. So 76.5% of the people that graduated are going to be happy with their job. Okay, now did not graduate, so I would go to this branch, and they're happy with their job. So just follow along with what it says. So didn't graduate is the 0.15, not, oh, and they're happy with their job, that's the 0.6. So to get that correct probability, we just multiply those guys together. This is 0.09, so that'd be 9%. Oh, I hope I didn't write too big. I'm going to try and keep this on the screen. All right, now, this, you're not going to need to multiply anything here. This will be like the table. Okay, given, this says they're happy with their job given that they graduated. So given that they graduated, I'm not even going to look at the bottom part of the table. So given, I picked one of the graduated people, and you don't need the beginning, just the fact that they were graduated. What is the probability you'd be happy with your job if you were given that they graduated? You don't have to multiply anything. If I give you that they graduated, what's the probability they'd be happy with their job? 0.9. Done. That's literally it. So the conditional probability can be a little bit easier than actually calculating what we just looked at. Okay, given that I didn't graduate, so we're just going to look at the bottom part of the table, did not graduate, that they're happy with their job. What would your probability be? 0.6. That's it. Done. Is anybody having a question? Okay, now this last example, this is kind of the weirdest format of all of these, I think, but you can calculate these conditional probabilities, but you have to really like read the question. So these will, you're going to look over here. It says find the following probabilities using this information. So I'm going to try and read this really carefully. Okay, 39% of people that you survey here have a pet now, and they have had one in the past. Okay, 61% don't have a pet now, 86% have a pet, and then 14% don't have a pet and have never had a pet. Okay, now this says the probability given that they have had a pet that they currently have one. All right, so this one says I have a pet now and I have had one. This one says I have had a pet, so these can be tricky. So given that they have had a pet, you just put that percentage on the bottom. Put the 86 on the bottom, and that they have a pet now, the 39 goes on the top. That's all you have to do. Okay, now for the other one here, don't have a pet, so don't have a pet, that's the 61. So that goes on the bottom. Whatever you're given, just put that on the bottom. And then they have never had a pet, that's going to be this 14. You can write the decimals or leave them as fractions, whatever your preference is. So the Math Excel is going to be super similar to this. Please let me know if you have a question. We have a ton of time today. If anybody needs help with yesterday's assignment, it's still open, and I'll be happy to help you with that too, but hopefully we'll get most of this done before you even go. I think there's 15, I want to say there's 15 total problems. And then just remember you guys have the